Hey y'all, I hope everything is going well with y'all so far today. So what we're going to be doing today is looking at manometers, and this is on page 17 of your book for Unit 3. So I think a good place to start off with is just thinking about what a manometer actually is. A manometer is actually just a tube of mercury that's used to measure pressure. And when I was going to school, we actually called these U-tubes, and that's because they're literally U-shaped tubes filled with mercury. So the mercury is the red liquid I've drawn here. Because remember, mercury is one of a handful of metal elements that are liquid at room temperature. The other one that I can think of is bromine. Is it bromine? Actually, I think it might be a different one. Anyway, that's not important. So, the first type of manometer we're going to look at is an open-ended manometer. And an open-ended manometer is simply a container of gas that's attached to one side of the U-tube, and then the other side of the U-tube is left open to the atmosphere. So what we pretty much have with an open-ended manometer is the gas in the container is going to be pushing down on the fluid on this side of the tube, and on this side of the tube the pressure of the atmosphere is going to be pressing down. So pretty much with all of these open-ended manometers, you're going to have a gas on one side pushing down on the fluid on one side, and then you're going to have the atmosphere pushing down on the fluid on the other side of the tube. Okay, so I've just written that there. Gas A exerts a pressure on the fluid on the left-hand side, and then the atmosphere exerts a pressure on the fluid on the right-hand side. And it doesn't matter what side they're on, so you might have the gas attached to the right-hand side or the left-hand side. It doesn't really matter. It's all arbitrary. So when we're talking about open-ended manometers, we have three different scenarios, and I've drawn those here. So the first scenario we have is this scenario here, where if we look at the manometer, we can see that the level of the fluid is the same on both sides. Okay, so in scenario 1, we can see that the height of the fluid is the same on both sides. Okay. So because the height of the fluid is the same on both sides, that means the pressure is equal on both sides because no side is being pushed on harder. Okay, so the pressure is equal on both sides. Okay. Because no gas is pushing harder than the other. Okay. So if we look at this scenario, for example, we're going to have the gas on the left-hand side pushing on the fluid from this end, and on this end we're going to have the atmosphere pressing on the fluid on this side. So because the fluid is even on both sides, that means the pressure that both the atmosphere is exerting and the pressure that the gas on this side is exerting is the same. So if we look at scenario number 2, we can see that the level of the fluid on the right-hand side is higher than on the left-hand side. Okay, so we'd say the height of the fluid is lower on the side of the gas. Okay, so there's a pressure difference because the gas on the left-hand side is pushing harder on the liquid on the right-hand side. So you can sort of think of it like this, right? So we know that the pressure from the atmosphere is pushing down on this side, and that the pressure from the gas is pushing down on this side. So we can tell, because the level of fluid is different, that the gas is pushing harder on the fluid than the atmosphere is, and that's causing this difference in height. So in this scenario, the gas is pushing harder than the atmosphere. And what we're going to see in a little while, that means that because the gas is pushing harder than the atmosphere, that the pressure of this gas is greater than atmospheric pressure. Okay, and let's look at example number 3. So in this case, the level of fluid is higher on the gas side. So again, if we look at this right, we know that the pressure from the atmosphere is pressing on this side, and the pressure from the gas is pushing on this side. But because the level of fluid is lower on this side, that must mean that the atmosphere is pushing harder on the liquid than the gas is. So the big takeaway here is that when the level of liquid is the same, the pressure is the same, but whenever there's a difference in levels between the two sides, there's a pressure difference. So I'll just write that here. When levels are the same, the pressure is equal. Yeah. And when there is a difference in height, there is a pressure difference. Okay, so that's the big takeaway for that so far. So now what we're going to do is just have a look at a couple more of these scenarios and have a close think about what the pressures actually are going to be. So if we look at example number 2 again, okay, so where we have our this doesn't look very good. Yep, so if we have scenario 2 here, that's going to look like this. Just going to quickly draw in the mercury. So this is going to be the gas. Let's just say gas A, and this is going to be that open to the atmosphere, obviously. So what we're going to want to do is look at the pressure of the gas and pretty much calculate it. So what we can see here in a situation like this is that the level of fluid is higher on the atmospheric side. So because of that, we know that the gas is pushing harder on the fluid than the atmosphere is. Okay. And we know that the pressure that the atmosphere exerts on a liquid is always going to be around a constant value. And we know that constant value is going to be 760 millimeters of mercury. So that's pretty much a constant. So we know that the atmosphere is exerting a pressure of 760 millimeters of mercury onto the fluid. But we know that the gas is exerting a higher pressure than that because the level is lower on this side. So the way we can calculate the pressure that the gas is exerting is to look at the difference in height of the two levels, and we call this delta H. And keep in mind we use a lowercase h opposed to an uppercase H, because if you say delta capital H, that actually means something entirely different. So let's just say we measured it for this example, that the difference in height between the level of fluid on both sides, let's just say that was 15 millimeters of mercury. So in order to calculate the pressure of the gas, we know that the pressure of the gas is going to have to be greater than 760 because it's pushing the fluid down harder than the atmosphere is. So it's going to be 760 millimeters of mercury plus 15 millimeters of mercury. And that'll tell us that the pressure of the gas in the container is therefore 775 millimeters of mercury. So now that we've just done some quick drawings there, I'm just going to walk you through filling out your booklet, and then that'll be a great opportunity for us to sort of recap all of the stuff we've done so far. Okay. Okay, so again, this is on page 17, by the way. So again, a manometer is an instrument that's used to measure gas pressure in an open or closed container. Okay, so when both sides of the U-tube are open to the air, the levels of the liquid on both sides of the U-tube will be equal. And this is because if both sides of the tube are open, they're both going to be having a pressure exerted upon them by the atmosphere, and the atmospheric pressure is constant. So on neither side of the tube will there be more or less pushing, pretty much. And when one end is connected to a sample of gas, three possibilities occur. And again, we said when one end is connected to a sample of gas that it's called an open-ended manometer. Okay, so let's look at this example here. So it says pressure of gas is greater than atmospheric pressure. So we can see that, right? We can see the pressure of the atmosphere is pushing down on the fluid on this side of the U-tube. And on this side of the U-tube, the pressure of the gas is pushing down. And because the level of fluid is lower on the gas side, we know that the gas is exerting a greater pressure on the fluid than the atmosphere is. So the column of mercury will be lower on the side of the gas and then higher on the other. So again, the difference in height here between this side and this side, we're told, is 50 millimeters of mercury. So to calculate the pressure that the gas is exerting on this side, it's going to be the atmospheric pressure, which is always going to be 760 millimeters of mercury, plus the difference in height, which is 50, so that gives us 810. And then on this side as well, we have it where the atmospheric pressure is going to be greater than the pressure of the gas because the liquid level is lower on the side of the tube where the atmosphere is pushing down on. So the liquid level will be higher on the side of the gas and lower on the side open to the atmosphere. And again, here we see delta H, they're telling us is 50 millimeters of mercury. And the pressure of the gas is going to be the atmospheric pressure minus delta H, because obviously the pressure that the gas is exerting on the fluid is going to have to be less than atmospheric pressure since the liquid level is lower on the atmospheric side. Okay, and then the pressure of the gas can be equal to atmospheric pressure, in which case there'll be no difference. So the level on both sides will be equal. Okay, and we can also get what we would call a closed-ended manometer, which is pretty much where instead of the other side being open to the atmosphere, it's just a vacuum. And remember, a vacuum is a container that has absolutely no matter in it. So in this case, we just simply need to use delta H to calculate the pressure. So we simply determine the difference between the two arms. Okay, so we're just going to do some examples really quick. So on page 19, it says the following manometers are open, and it's important to note that they're open, so that means they're going to be open to the atmosphere. And they're telling us here that the atmospheric pressure they're giving us in kilopascals. Okay, hi again. So the camera actually just cut off midway through in that other video. So I just thought I would start a second video just to go over some of the worksheet examples on page 19. So this is a good way to practice what we've learned so far and also do some of the conversions between some different units of pressure. So if we look on page 19, it says the following manometers are open. So again, what that means is one side is connected to a container of gas, and the other side of the tube is left open to the atmosphere. So we're told here that the pressure of the atmosphere is 102 kilopascals. Okay, and we're told the two heights of the fluid on both sides. So on this side of the tube, it's 230 millimeters of mercury, and on this side, it's 550 millimeters of mercury. So the first thing that we need to do is calculate the difference in height between the two arms. So to do that, we're just going to take the bigger number and then subtract the smaller number. So that's going to be 550 minus 230, which is going to be 320. Okay, yeah, so the difference in arms is 320 millimeters of mercury. So what we need to do as well is convert the difference in arms from millimeters of mercury to kilopascals, because it wants us to give us that pressure in kilopascals. So to convert 320 millimeters of mercury to kilopascals, remember we take what we have and we multiply it by what we want to gain, divided by what we want to lose, and that'll give us what we want. So we have 320 millimeters of mercury. We want to gain kilopascals, and we want to lose what we have, which is millimeters of mercury. So we're just going to put in our conversion factor. So it turns out that 101.3 kilopascals gives us 760 millimeters of mercury. Okay, so the millimeters of mercury cancel, and then we're just left with kilopascals. So there'll be 320 multiplied by 101.3 divided by 760. So that'll give us 42.65 kilopascals. So we know that's what the difference of the fluid level is in kilopascals. So to find the pressure of the gas is going to be higher than the pressure of the atmosphere because the gas is pushing harder on the fluid than the atmosphere is. So the pressure of the gas is going to be the pressure of the atmosphere, which they tell us is 102 kilopascals, plus the difference, which is 42.65 kilopascals. So that'll give us 144.65 kilopascals. Okay, and remember in the last video we were saying that the atmospheric pressure is 760 millimeters of mercury. So usually that equates to 101.3 kilopascals exactly, but the atmospheric pressure does change with altitude. So the atmospheric pressure that they give you is the one that you need to use. If they don't give you an atmospheric pressure, then it's fair to assume that it's 760 millimeters of mercury or 101.3 kilopascals. So let's look at example 2. So they've given us the atmospheric pressure again in kilopascals. So the first thing we need to do is calculate the difference in height in the arms. So we're going to call that delta H. Instead of writing out difference in arms, we're just going to write delta H, which means difference in height. So that's going to be 350 millimeters of mercury minus 120 millimeters of mercury, which is going to give us 350 minus 120. That's going to give us 230 millimeters of mercury. So now that we have our difference in arm height, or our delta H in millimeters of mercury, because they've given us the atmospheric pressure in kilopascals, we're going to convert our delta H into kilopascals. So remember, it's what we have, which is 230 millimeters of mercury times by what we want, what we want to gain, which is kilopascals, and what we want to lose is millimeters of mercury. So remember, the conversion factor is 101.3 kilopascals to 760 millimeters of mercury. So we times 230 by 101.3 divide by 760, and then we're going to get 30.66 kilopascals. This time the pressure of the gas is going to be less than the pressure of the atmosphere, since the gas is pushing less hardly on the liquid than the atmosphere is. So P gas is going to be the atmospheric pressure, which they tell us is 103.4 kilopascals, minus, not plus, 30.66. That's 103.4 minus 30.66. So that'll give us 72.74 kilopascals. Okay, so just to quickly recap a really important point here. So just keep in mind, if the level of the fluid is less on the gas side than the atmospheric side, like we can see here, the pressure of the gas is going to be greater than atmospheric pressure. So P gas in this scenario is 144.65 compared to 102 for the atmosphere. So just doing that in your head quickly should allow you to check whether you're right or wrong. So for number 2, we can see the level of fluid is higher on the gas side. So this must mean that the pressure of the gas is less than atmospheric pressure. So we said that the pressure of the gas is 72.74, which makes sense because again it's less than the atmospheric pressure since it's pushing less hardly on the fluid than the atmosphere is. Okay, so we're just going to do example number 3 really quick, and then you're free to do some of the practice questions on the next page. Okay, so for this one we can see that the level of fluid is the same on both sides. Right, we can see that here. So delta H would be 0 millimeters of mercury. So, because the level of fluid is the same on both sides, we know that the pressure of the gas must equal the pressure of the atmosphere, because if they weren't the same, there would be a difference in height. So because there isn't a difference in height, the atmosphere is pushing on the liquid just as hard as the gas is pushing on it, so that must mean they're exerting the same pressure, so you don't even need to do a conversion factor. Pressure of the gas is just going to be pressure of the atmosphere, which they tell us is 101.9. Okay, so on page 20 there's just a few other examples you can take a look at, and then you can do some of the questions on page 21 that have the answers on the bottom as well.